My talk titled Training Neural Network for Machine Intelligence in Automatic Test Pattern Generator. My name is Soham Roy and I am a PhD candidate of Electrical and Computer Engineering Department at Auburn University in Auburn, Alabama, USA, under the supervision of Professor Spencer Millikan and Professor Vishwani Agarwal. Today, I am going to give you some prior work and motivation for this study. Then, I will explain how machine intelligence is applied to our study. I'll also discuss about the possible directions leading to a formal training procedure of the artificial neural network. I'll then discuss on how we resolve conflicted training data patterns using some trivial mathematical calculations, followed by the proposed recursive training algorithm which makes our ANN an evolving ANN. I will also analyze our experimental results thoroughly. Finally, I will conclude this talk by briefly point out the major contributions of this study and future avenues that may be taken to achieve more interesting results. The D algorithm in 1967 established ATPG as a standard method of generating high-quality tests for the logic circuit industry. However, since its introduction, it was noticed that ATPG can have frustratingly long runtimes for some circuits. Numerous later studies lowered ATPG runtime in numerous ways, but since the introduction of BODEM in 1981, the theoretical upper limit of ATPG runtime has remained constant. Let us see an example. For a circuit with I inputs, these I may include scan latches in case of scan-induced circuits. ATPG may need to simulate 2 raised to the power number of primary inputs of the circuit vectors to find a test. Although ATPG algorithms typically find tests without simulating close to this many vectors, this upper bound still exists and is occasionally seen in modern circuits. To avoid this upper limit, most ATPG algorithms employ backtracing subroutines. These subroutines trace backwards through a circuit starting from an objective, such as exciting or propagating a fault, and attempt to find input assignments which accomplish the objective. Multiple backtraces from an objective may be required to meet the objective. But if these input assignments accomplish the final goal, that is find a test for the fault, then at most I input vectors must be simulated, which is nothing compared to the theoretical maximum of 2 to the power I. However, this ideal situation presumes no backtracks occur during ATPG. When the backtracing subroutines reach a circuit input and assign it a value, this assignment may block the current or future objectives. When this occurs, ATPG must undo or backtrack to some previous assignment, which means ATPG wastes time simulating unnecessary input vectors. Beyond BODEM, numerous ATPG algorithms attempt to reduce runtime by creating fewer objectives, but to our knowledge, no studies compare ways of backtracing from an objective. When backtracing, it must decide which direction to go, but choosing a wrong direction may result in a backtrack. To develop a new backtracing strategy, I look towards the technology of machine intelligence. Machine intelligence describes a broad category of algorithms that automatically program themselves through experience. This experience can come from unclassified data which the program finds patterns in, which is unsupervised learning, or the experience can come from a database of training problems with desired outcomes, which is supervised learning, or the experience can come from iterative re-evaluation and adjustment, which is reinforced learning. Recently, International Test Conference ITC 2020 published our research work which shows that an artificial neural network ANN can combine multiple heuristics to guide an automatic test pattern generator ATPG with fewer backtracks than required by guidance from any single heuristic. We are going to reuse same ANN structure that has a single output neuron and a single layer of hidden neurons, which is sufficient to accommodate the training data volume. Conventional BODEM ATPG applied to hard-to-detect and easily detectable faults in selected benchmark circuits provide training data for nodes marked as success if the backtrace leads to a test, or failure if it results in backtrack. Each entry in the training data pattern comprises of the COP controllability, the circuit depth, and the driving gate type given as a one-hot string on the decision point. Let us try to figure out the motivation of this study. These are the results we obtained from our own work of ITC 2020. If the backtrace leads to a test, results depend heavily on benchmark sizes. We chose to normalize plots. Each entry in the training data pattern comprises of the COP controllability, the circuit depth, more accurately reflect the goal of ATPG given as a one-hot string, that is to reduce the decision point by a factor as opposed to by a constant. Let us try to figure out the motivation of this study. These are the results we obtained from our own work of ITC 2020. If the backtrace leads to results on decreasing the backtrace on benchmark analysis, we chose to normalize most benchmarks respecting a data pattern in comprises of the COP control. We believe the decreases more accurately reflect the goal of given as a one-half strain, that is to reduce decision as we can also see that the improvement in ATPG performance. Let us try to figure out the motivation of this study, including some larger results we obtained from our own work of ITC 2020. The backtrace leads the results on decreasing backtrace on benchmark analysis we chose to did not perform well. To motivate this work, we repeated the work of ITC with minor changes. Firstly, training patterns were generated using PODEM applied to 100 hard-to-detect faults in the 3 highest depth circuits, that is C6288, C3540, and B05. Secondly, the trained ANN was then used to guide a PODEM applied to the 100 hardest to detect faults in each of the 24 benchmark circuits used in the original ANN, that is ITC studies ANN. This figure compares the total backtracks with those of conventional PODEM using distance and COP heuristics. One difference in our evaluation procedure, as stated in the ITC study, is that we did not include backtracks from aborted faults. We refer ITC studies ANN as the original ANN to distinguish it from the ANN developed in this study identified as the new ANN. The ANN training in the ITC research study was ad hoc and rudimentary. Therefore, this study provides a formal training that may elevate ANN-guided PODEMs at performance. This study examines such a training method. The training recursively uses ATPG data generated from hardest to detect as well as easily testable faults, resolves conflicts in data patterns, example when different ANN outputs come from similar inputs, and discards data in this study identify the guidance of ANN. We believe remedying the outliers just mentioned few slides before requires addressing several aspects of the ANN training procedure. Our investigation led us into following observations. Firstly, the ANN was trained with ATPG data from high-depth circuits. Since C3540 causes worry, I retrained the ANN with just 3540, but still the ATPG performance of this circuit did not improve. Therefore, I retained the 3 high-depth circuits for training. Secondly, the training data patterns may lead to increase in training error of the ANN and thus degrade its guiding ability. This is explained in details in upcoming slides. Thirdly, all faults do not provide useful training information, and pre-selection of faults for training may unnecessarily increase the training data volume without benefit. Upcoming slides gives a novel method of training the ANN considering 3 aspects. That is, the training error of ANN must be kept low by adjusting the number of hidden neurons. Training data from a fault must be accepted only if guidance from the resulting ANN reduces backtracks, and the faults used for training data generation should not restricted to be hard to detect faults. In fact, a fault provides useful training data as long as it reduces backtracks. And finally, the ANN may enter a zone called catastrophic forgetting when it forgets information contained in a large training data volume. Such consideration in training improvement is worth exploring in the future. To remedy conflicting training data patterns, we collect patterns with identical features into groups and then replace each group by a single representative pattern with common features. Since these patterns are derived from actual ATPG runs, the label of a pattern is either 1 indicating success if it belongs in a backtrace leading to a test, or 0 indicating failure if it results in a backtrack. We count the number of 1 and 0 labels in the group, and the representative patterns label is given in the next slide based on a formula. In this slide, a conflict is illustrated by the sample training patterns in figure where the first 3 patterns have a conflict. This is resolved in this figure where the 3 patterns are replaced by a single representative pattern with a label count equals 1 divided by number of label 1s plus number of label 0. That is 2 divided by 2 plus 1 equals 0.67. The algorithm is to develop an evolving ANN-guided ATPG is illustrated in the figure. We select large depth circuits C6288, B05, and C3540 from ISCAS 85 and ITC 99 benchmarks. The ANN structure is same as in the ITC recent study, and parameters such as number of hidden neurons and mean square error are initialized. COP-based PODEM is applied to a set of 100 hard-to-detect faults, and number of backtracks is recorded to be minimized through recursive learning. The training starts by using 50 hard-to-detect faults to generate a training database, followed by ANN training to check mean square error and record the corresponding number of hidden neurons simultaneously. This process continues until mean square error starts saturating and corresponding mean square error and the number of hidden neurons are recorded and the ANN is retrained. The similar process is continued for 100 easy-to-detect faults To evaluate the training, the ANN guided ETPG is applied to 100 hard to detect faults of the same training circuit. If backtrack count decreases, then 100 more hard and easy to detect faults are added to the training of the ANN as the number of hidden neurons and mean square error are restored. Discarding the corresponding training patterns from the training database, and another circuit is selected to reiterate the same process until one of the following conditions is satisfied. We kept these conditions to satisfy our need, but one can always change these conditions. These conditions are the number of backtracks should be reduced to at least 50, at most 100 hard and easy to detect faults should be used for training, and finally the ANN contains at most 100 hidden neurons. The graph shows how the
So, Miss Dipali, you have any questions?
Zalak, no, I don't have any questions received here.
Okay. Dipali, just make up a question. Ask me what is a complete closed circuit. I will tell you the answer.
Yeah, Zalak, please tell me what is that circuit? No, because the half of the time that CPU was like off for me due to internet issues.
Yeah, so a circuit is something which, when gets completed, your light and bulb goes on.
Okay.
Okay, Ishwar. But it was nice. Yeah, it was coming out nicely. I even tried watching it on the side, the way it is being displayed, and it was looking good.
Yeah.
So, yeah.
I have now.